all about these organic structures, right? So what we did last time was we simplified these rules for drawing Lewis structures into just this bonding pattern cheat sheet here, where we said as long as each element has this certain number of bonds and this certain numbers of lone pairs, we know that it's happy, okay? And we said that this is how many bonds and lone pairs an element likes to have, all right? So what do we mean by likes to have? Well, importantly, that's going to correspond to this next concept here, what's called formal charge. All right. All atoms, they like to have, i.e. they are most stable, when they have a formal charge of 0. Okay, so when we built that little cheat sheet before and we said this is how many bonds and this is how many lone pairs an element likes to have, what we were really doing is making a chart of how many bonds and how many lone pairs an element has when it has this formal charge of 0. All right? Now, that's great. That is indeed the most stable state of all of those atoms. However, usually chemistry doesn't happen between two super stable molecules, right? Oftentimes the most interesting aspects of chemistry is because there's some degree of instability going on. So oftentimes we will see formal charges that are involved in our organic reactions. So first of all, what exactly is a formal charge? A formal charge gives you an idea of the amount of electron density that's sitting on that atom, okay? So our formal charge here is going to be a measure of the electron density on a given atom. So, for example, if we had OH minus here, what is OH minus? Yeah, we remember this from general chemistry. This is our hydroxide ion here. Very famous, strong base. If we're going to draw the formula for our hydroxide, rather the Lewis structure for our hydroxide ion, what we're going to see is our oxygen only has one bond to that hydrogen atom, right? And how many bonds do we say oxygen likes to have? Two bonds and 2 lone pairs. Well, now it only has 1, and it still has to have that complete octet. So instead, now it has 3 lone pairs, and this negative charge on that hydroxide ion, it's a little bit deceptive when we draw our chemical formula here. That negative charge is actually sitting on that oxygen atom. All right, this is this formal charge associated with this oxygen atom in this hydroxide compound. So this negative charge that I put here, this is the formal charge. And in this case, this Lewis structure is demonstrating that in this molecule, in this hydroxide ion, that negative charge specifically lives on that oxygen atom. All right? So, similar to how we had these bonding patterns that told us how many bonds and lone pairs an element likes to have, what we just refined as meaning has a formal charge of 0, we're going to build ourselves some similar bonding pattern cheat sheets here. We'll call these our formal charge cheat sheets. All right, and so let's go ahead and take oxygen as our first example. Okay, again, we're going to make a little chart here. We're just going to include one more entry, which is going to be formal charge. So formal charge, number of bonds, and number of lone pairs. this little chart here, we're going to have 3 columns. What we're going to see is our nonmetals, at least in organic chemistry, they only really adopt 3 different charge states. Okay, so let's put in the middle here what we said oxygen likes to have. It's 2 bonds and it's 2 lone pairs, right? And remember, when we said it likes to have, that means its formal charge would be 0. Okay, so if we just want to draw a little example up top here, we'll draw our oxygen with its 2 bonds and its 2 lone pairs. Nice and happy, formal charge is 0. All right, now what I'm going to do is I'm going to take one of these bonds and I'm going to turn it into a lone pair. All right, so now I'm going to decrease my number of bonds and increase my number of lone pairs. All right, again, I converted one of these bonds into a lone pair here. So let's think what's that going to do to our formal charge here. All right, I took this bond, this shared pair of electrons. So it used to be a pair of electrons. Oxygen was sharing with some other atom. And I picked it up, and now I put it directly on that oxygen atom. Is that going to increase the amount of electron density or decrease the amount of electron density on that oxygen? Turning that shared pair of electrons into one only sitting on oxygen. Increase or decrease electron density? What do we think? Increase electron density. Okay, and if I have an increase in electron density, is that going to be a negative charge or a positive charge? Negative charge, right? So if we take one of those bonds and we turn it into a lone pair, we increase electron density, decreasing that formal charge, right? And again, if I want to do a little example, I will have my oxygen with its 3 lone pairs and 1 bond. All right, in addition, for formal charges, we always are going to include that sign, that charge, on that atom. You don't have to put a little circle around it, but just to make a point, I'm going to put a little circle around it. All right, and what if I do the exact opposite? What if I turn a lone pair into a bond? So a pair of electrons that was just sitting on oxygen is now being shared with some other atom. Is that going to increase or decrease electron density? Decrease. So now I have a +1 formal charge. All right, so this would be oxygen now with 3 bonds and just 1 lone pair. That would give it a formal charge of +1. Right? And these are the only formal charges that we're going to see in organic chemistry, either 0, +1, or -1. Unlike inorganic chemistry, unlike ionic compounds where oxygen can adopt a -2 charge, that's bonkers in organic chemistry. You will never see oxygen with a -2 charge, right? So the only formal charges that we'll see are +1 and -1. Kind of did that backwards. But yes, +1 and -1. And that's true for pretty much all of our elements here. So we're going to do the same thing. We made a little cheat sheet for oxygen. Let's go to nitrogen. All right, we'll build a little cheat sheet for nitrogen as well. Same chart here. All right, nitrogen likes to have 3 bonds and 1 lone pair, meaning it has that formal charge of 0. Given what we just did with oxygen, given that same logic of what happens when we convert bonds into lone pairs or vice versa, I want y'all to try to fill in the rest of this chart here. one of those bonds into a lone pair, what's going to happen to our formal charge? It's going to decrease to -1, so nitrogen with 2 bonds and 2 lone pairs. This would be nitrogen with this negative formal charge. And likewise, if I converted one of those lone pairs into a bond, so now all of a sudden I got 4 bonds and 0 lone pairs, this would be nitrogen with a formal charge of +1. Let's do our halogens now. Okay, so I'm going to copy my same chart here, but now fill it in for one of these halogens. We'll use fluorine as our example halogen. I'm going to leave this one for y'all to do on your own here. Again, we noted that a halogen likes to have 1 bond and 3 lone pairs. All right, so you're going to fill in the remainder of this chart. The one that I want to go over next specifically is the star of organic chemistry, and that is carbon. Okay. Carbon's a little weird, and we'll see why here in a second. At first, everything looks normal. If I'm going to do carbon with a formal charge of 0, as we noted, carbon likes to have 4 bonds and no lone pairs. All right, carbon will also adopt a formal charge of -1, so take a second and fill out this column here for carbon when it has this -1 charge. All right, just like before, I'm going to turn one of those bonds into a lone pair. All right, so carbon with 3 bonds and a lone pair will have a minus charge. All right, so first of all, because this is carbon and because carbon is the star of the show, we have a special name for this ion here. Right? Our negatively charged ions. Does anybody remember cation or anion? What's the negatively charged ones? Anion. Okay, so this here we have a special name for. This we call a carbanion because it's carbon and it's an anion. Gets a special name. All right, but carbon can also adopt a +1 formal charge, but all of a sudden our trends that we've been seeing are going to break down, right? In every other instance here, we converted a lone pair into a bond, and that's how we increased that formal charge. We don't have any lone pairs to work with here. So how are we going to do this? Okay, well this is what's going to make this really unique. If we go back up, one of the things that I want to note about every example that we've done is if you total the number of valence electrons, it's always 8. So oxygen, when it's neutral, form 8 electrons in its octet. When it's got a -1 charge, still has that complete octet. When it has a +1 formal charge, still has a complete octet, right? 6 electrons in bonds, 2 in lone pairs. So my oxygen always has a complete octet. We're just going to note Always a complete octet. Nitrogen, same deal. Total up the number of electrons in its valence shell, right? 2 for every lone pair and 2 for every bond. You'll see it always has a complete octet. Our halogens, when you complete this chart, you can convince yourself it always has a complete octet. All right? If we look at carbon with its +1 charge, carbon will have 3 bonds but 0 lone pairs. And that means that this positively charged carbon has an incomplete octet. All right, here they're complete. But that positively charged carbon has just 3 bonds, no lone pairs on it, thus having that incomplete octet. All right, so first of all, we got another special name. If it was negatively charged, we call it a carbanion. When it's positively charged, we call it a carbocation. So our carbocations, nice and stable. No. Is anything with a formal charge nice and stable? No, not really. Atoms don't like to have a formal charge. Oftentimes you can coax it into having one given the conditions, but a carbocation is especially pissed off because not only does it have a formal charge, it also has this incomplete octet. All right? Nonetheless, that doesn't mean that we never see it. In fact, we will see carbocations quite frequently, but they're just these short-lived intermediates in our chemical reactions, right? So these unstable species here, just because they're unstable doesn't mean they don't matter, all right? Good advice for life as well, all right? We will still see these unstable species playing a very important role in the chemistry of these atoms, of these molecules, all right? So number one, being able to recognize these formal charge patterns. That's going to be the most important important part of what we're going over here. We don't even know why this is important yet with regard to reactions. We haven't quite gotten there. We're just making sure that we can recognize atoms when they have these formal charges. And again, we have these bonding patterns. Okay? So just to practice here, you're going to complete this structure by filling in any missing lone pairs and formal charges. Oh, you don't know that. I'm sorry. We haven't gotten them online yet. Getting ahead of myself here. so doing this one here, zooming on in. I see this oxygen. This oxygen only has one bond, so how many lone pairs am I going to have to add to complete its octet? 3, because oxygen always has a complete octet. With the exception of carbon, you will never see any of these elements with an incomplete octet. And if it's got one bond and 3 lone pairs, then I know it has a formal charge of -1. Right? Now we've got one extra lone pair compared to, and one fewer bond and one extra lone pair compared to what it likes to have, so we have more electron density on there. All right, and am I done? No, I got another one of these, what we call heteroatoms. So in organic chemistry, anything that isn't carbon or hydrogen is considered a heteroatom. So how many lone pairs do I need to put on my nitrogen here? 1 to complete its octet, which means its formal charge would be 0. All right, so this is its happy bonding pattern here. So this particular nitrogen has a formal charge of 0. Going over here, again looking at my heteroatoms, nitrogen and fluorine. My nitrogen is going to need how many lone pairs to complete its octet? None. It's already got 1, 2, 3, 4 bonds. Okay? And since it's got 4 bonds and no lone pairs, that means it's got a formal charge of +1. All right, my halogen here, fluorine, has 1 bond, so I'm going to need to complete its octet with 3 lone pairs. And that would be a formal charge of 0. That's fluorine's happy state right there. Okay? So filling in these missing lone pairs and formal charges, making sure that we can recognize when we have a formal charge is going to be important. All right, so we've been representing these molecules with these Lewis structures here. I kind of accidentally gave you a preview of one of these types of structural representations that we're going to be doing here, what's called a bond line structure. But let's just put these down here. I want to summarize it, and I'm going to show you them first, and then we'll go back and pick them apart. How did I get these? Okay? But these are these different structural representations that we're going to use. All right, so first of all, as we said at the very beginning, we have our molecular formula or our chemical formula. So for example, the C2H6O. And as we said, we're pretty much never going to just use a chemical formula because this is not enough information. All right, this was the example last class where we took this one chemical formula and we were able to draw these 2 distinct molecules, right? What we call 2 constitutional isomers. Molecules that shared the same chemical formula but had a completely different connectivity of atoms, right? They were themselves distinct molecules. So again, chemical formulas, not enough information. All right, we also have our Lewis structures. That's what y'all were introduced to in general chemistry. That's what we've sort of been using up until this point. All right, so just a reminder, we had these 2 Lewis structures for this same molecule. One where my, what we call our backbone is carbon, carbon, and then oxygen. Or we could have carbon, then oxygen in the middle, then another carbon on the end. So these were these 2 Lewis structures. And Lewis structures are great in the sense that we do get every bit of structural information that we could ever need from these pictures here. They're just a pain in the butt to draw, right? And especially if you have a big, complicated molecule. As soon as you get too many carbons or too many branch points in there, all of a sudden it gets to be just way too much on the page. To when you look at it, you really don't get very much information from it. It's just too much going on. Your brain can't really process, all right? So we have other more simplified ways that we're going to use. The first is what's called a condensed structure. All right, or sometimes a condensed structural formula. This is something that's going to be really important to read. I'm not going to be too concerned with your ability to write these out, but more that you can interpret them when you see them, all right? This is because this is the preferred format of like books and databases, because it's the way that we're going to be able to represent our structure all in one line, right? So as if I was typing it into a computer or something like that. I can't exactly draw a Lewis structure on my keyboard. I mean, there are little fancy programs that we can use, but if I'm typing something in, I can't do a Lewis structure. So instead we have these condensed structural formulas that we're going to use. And the whole point of a condensed structure is we're going to see it's kind of like a molecular formula, but it's going to give me information about the structure of that molecule as well. All right? So our condensed structural formula for this molecule here would be CH3, CH2, OH. All right, and so we can see how each segment of this molecule, CH3, CH2, OH, is represented in our condensed structural formula here. Okay? And again, the whole point is it's going to tell us about our structure. So if I did the condensed structural formula for this molecule, it would be different. This molecule over here would be CH3O, CH3. All right, where again, I'm sort of representing each little component. Here's my first CH3. Here's my oxygen in the middle. Here's my other CH3, right? And so notice that these two distinct molecules, they have these two distinct condensed structures, okay? Since this is like a typing database kind of thing, you could, but we don't really include lone pairs on there, because again, we're not really using these, I will say, we won't see these too often as being used like in lecture, in class. Again, there's something like you're going to encounter something in a textbook and it's going to describe a molecule in this formula and you just need to be able to interpret it, right? So that's going to be my goal for y'all is to be able to read these condensed formulas here rather than writing them. There's not necessarily one right way to write a condensed structural formula. The one that we're going to use throughout the remainder of the semester is what's called a bond line structure. And y'all can just trust me for right now, but let me just show you the bond line structure of this molecule here. All right, it would look like this. Okay, this molecule here, I would represent using this bond line structure. You guys don't know how I got this yet. We'll pick this apart, we'll lay out rules for drawing these bond line structures. But just know, why do we love them? Because how long did it take me to draw that structure? Like 0.2 seconds, right? Boom, boom, squiggly lines, done. And I can read this. I know how many carbons are there. I know how many hydrogens are there, all right? We're going to graduate to that. But this is what we're going to use throughout the remainder of the semester, are these bond line structures. These very quick ways of drawing our molecular structures. If I was going to do that for this molecule here, I would again have some line segments, but now my oxygen is sitting in the middle. Okay, so these are these three representations that we're going to use. Again, you don't know how I got this yet. We'll lay down some rules. All right, but Lewis structures, these, pain in the butt. You'll see them every once in a while, especially for very tiny molecules. They're fine. They're just a pain in the butt to draw. Condensed structures, you're going to see them a lot in books or anything that's typed out because they're a really convenient way to represent all in one line what a structure is. And then what we're going to be using over and over and over again are these bond line structures. All right? So let's take a look at our condensed structures first. So again, the whole point of a condensed structure is that it's going to allow us to represent the unique structure of a molecule all in one line. All right, specifically one line of text. All right, and importantly, I'm not too concerned with your ability to write these condensed structural formulas. Our goal is that you can read these condensed structural formulas. Interpreting them into either a Lewis structure or a bond line structure, right? You know the unique structure that's being represented. Okay? Our first and most important rule when interpreting these condensed structures is you must obey the octet rule. All right, there's a lot that's left implied by these structures because there's no other way to do it except for one way without breaking the octet rule. So if you draw it out, you think you're connecting the dots correctly, but you see that you've broken an octet rule. That's not how it is, right? So they're always going to maintain that octet rule. Okay? One of the ways that we're going to say that things get condensed is if we have repeating units. We can represent them, or rather, we're going to use parentheses with this subscript indicating how many we have. All right, so what do I mean by that? Let's say that we had this formula CH3 and then in parentheses CH2 with this subscript on the outside, 2. This means that we have 2 repeating units of CH2 in the middle there. So if I'm going to draw this out here, this would be C, H, 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 my CH3. Then I move on to the next carbon. Boom, boom. Move on to the next carbon. Boom, boom. I got 2 of those CH2s in the middle, followed by that last one. All right, so this, with that subscript of 2, represents these 2 repeating units of CH2s. And then we got a CH3 on one end, and we got a CH3 on the other end. Okay? You'll also see parentheses used in a different way. All right, so for large groups that are off the main chain, we'll also use parentheses but without a superscript, or rather without a subscript. All right, so for example, if we had CH3CH and then in parentheses OH CH3. Now there's no subscript on the outside here, so it's telling me that this OH group is pointing off of the main chain. All right, so if I'm going to draw my structure here, I have one CH3. I get to my next one, CH, and now I'm going to include that OH pointing off of that main chain before I get to my next CH3. All right, so again, just to kind of pick it apart, this first CH3 right here, then we get to the next unit, CH, but then I have in parentheses this OH that's pointing off of my main chain. And I should be good and put my lone pairs on my oxygen, because we're always going to be good and include lone pairs on our heteroatoms. All right, and then lastly, we got that last CH3, that's that unit right there. Okay? Cool. All right, so this is going to be kind of a practice makes perfect type of thing here. So let's just try to practice reading our condensed structures. Where am I? There we go. All right, so again, we're going to read these condensed structures, or rather, you're going to turn these condensed structures into Lewis structures. So I'm going to give you all a little bit of head start, and then I'm going to quietly start filling in the Lewis structures up here. Cool. All right, so just to go through these real quick, CH3, CH2, and then NH2, so that nitrogen is on the end of my molecule. Boom. Okay. My next one here, again, CH3. Now I get to my nitrogen in the middle of the molecule, but it's not in parentheses, so it's not pointed off of the main chain. It's sitting in the middle of the main chain. And then my last CH3 group. Just compare that to this fourth one here, where now that nitrogen is in parentheses. So if I were going to go down the line here, CH3, then I hit my CH, and those parentheses telling me that that nitrogen is off the middle of that main chain. And on the other side, my last CH3 here. Okay? And then this one here, we have our carbon in the middle, and then we have 4 repeating units of CH3. So in order to complete that carbon's octet, all 4 of them have to be off of that main chain. And you can already see how our Lewis structure is getting real busy here, right? You had to kind of creatively draw some of these lines longer than others in order to fit them into this structure here. And so we'll see why our bond line structure is far more convenient. But again, we want to be able to read these condensed structures here. So that's what you're going to be practicing on your homework. Cool. All right, we'll pick up with this next time. We'll go into that last structural representation, which is going to be